integration by parts. This is one method, but it's a little archaic. So in this video, I'll show you not how to use the integration by parts method, but rather how not to use it, just like we did with the substitution method. So it's u dv, the integral of u dv equals uv minus the integral of v du. Let's take a look at an example of why you might not want to use that, and instead use the other technique that we all know now is a lot better. It's the DI method. If you would try to integrate this thing using the DI method, it would probably, or sorry, the integration by parts method, it would probably take you maybe a half hour or something. But if you were to do this with the DI method, we can just do it real simply. So we're going to take the derivative of the x to the third, and we're going to integrate sine x. And so let's start writing our pluses and our minuses on the side here. I think we can have a couple of those. We'll go ahead and start with our x to the third, and then 3x squared, 6x, 6, and a 0. This is where we're able to stop. We'll head over to this one, the sine x, and then when we integrate that, we get negative cosine of x, and then we integrate that, we get negative sine x, and then cosine of x and sine x one more time. We can basically be done here. And all I'm going to do is draw some arrows, a couple of arrows here, and we'll quickly be able to figure out that the solution to this problem is just negative x to the third cosine of x plus 3x squared sine x, just multiplying these things together. 6x cosine, this is a plus right here, cosine of x, and then minus 6 sine x. I'm just trying to write pretty small here, But anyway, so we can just quickly get an answer instead of having to do any work. We have the answer to this integral. It's kind of incredible. Yeah, we do have some rules we have to follow. If we were to we want to figure out when do we stop. Sometimes there's situations when we want to stop. So for example, if we get 0 in the D column, then we're going to stop. If we have the, if we can integrate one of these rows, integrate this row, then we can stop. It's not an example here, but if you know how to use this method, then this is just some notes on it. And if the row repeats, then if you get the same thing like there and there, then we want to be stopping with this method. So this is just one of the methods that we would want to use. And this is in this type of situation, you're going to want to get a flashcard or a few flashcards, a couple different examples of when the DI method or the integration by parts method would be best suited. Just a whole bunch of different examples and stick them in the flashcard. And you don't have to solve these integrals. All you need is just put the DI method. That's the answer. And then you just say, okay, if I ever see integrals that look like this, I should just use the DI method. And then you'll just start to notice that there's certain patterns. All right. Why? Well, you'll just see why. It just works out because this is pretty easy to integrate a couple times. This is really easy to derive a couple of times, and you start thinking, oh yeah, okay, if I just do that, the DI method, that will just quickly solve itself. You can kind of do integrals in your head real quick like that, if you see what I mean. Now, let's just go ahead and also mention that we have the Liate thing that probably want to follow in this situation. So we'd be going log, inverse, algebraic. In this case, the algebraic function would be black here. And then we head over to the trig for the integral side and the exponent right over here. So exponential. This is what we would prefer to derive, to take the derivative of logs, inverse trig functions. This is inverse trig, by the way. Inverse trig. We prefer to take the derivations of the inverse trig, and then over on this side, we prefer to integrate trig functions or exponential functions. This is the integration by parts method. It's one of the easiest, most fun methods to integrate. So make sure to get this in your arsenal and get some flashcards and just start building up this list of a couple of different integrals that you can solve with the DI method. The next type of integration method you might want to use is the trig sub. Trig sub. So let's say we had some kind of cosine to some power x, sine x to some power, and then dx. Well, regardless of what kind of sine power you have here, you could say, hey, we've got u equals cosine x, and then du would be equal to sine x dx. And so basically, you can see how this could just kind of quickly replace these things and work out pretty nicely there. And so if we had maybe a sine squared x, then that would be equal to 1 minus cosine squared x, and then we would have maybe the sine squared x, depending on which type of solution will be best for the type of integral you're trying to solve. One of these two replacements for sine x should work. You might have another type of situation, maybe with secants and tangents, tangent to some kind of power, secant. Well, these ones might be a little bit more vague. You kind of have to play around with it. So, u equals secant x would leave you with a du equals secant x tan x dx. So that might replace it if you just have one tan x, if you're somewhere sitting around there. Or u equals tan x would be equal to like a du of secant squared x dx. So if you have a secant squared, that could replace it. These are just some ideas to solve this type of thing. And again, with these, you just want to get a couple examples of each of them, and then just write out this part of it that will give you the answer. Like, it's just like, okay, this would be the answer to that type of trig, that type of integral, and you put that in your list of flashcards. You don't have to solve these integrals. You just want to see what the technique would be to solve it, and then put it in your list of flashcards. So you start to recognize the patterns, because it's just all about the patterns. Now, we may end up with some type of situations where you have these weird associations of like ax sine and cosine bx. These are some identities that we just want to have these down as well. So these ones would just be something like 1/2 cosine of a minus b x minus 1/2 cosine of a plus b and then x. And then on this one, it would be 1/2 sine a minus b x plus 1/2 sine a plus b x. And on this one, it would also be 1/2 cosine a minus b x plus 1/2 cosine of a plus b x. Just some identities here. There's also this crazy stuff called the reduction formulas. So the reduction formulas of tan n minus 2 x dx. These are the reduction formulas just in case you have some high powers of n, the high powers of sine, cosine, secant, tangent. There's probably going to be some other ones too for the ones, but these are just the main ones, I suppose. These are the reduction formulas that you might want to have on your cheat sheet as well. Now let's try the easy stuff, the perfect squares. Perfect squares. These are some really easy techniques and some pretty cool setups. So let's see, we got the square root of a squared minus x squared. This is going to be, let's try to remember these identities. Cosine squared theta equals 1 minus sine squared theta, and then or sine squared theta equals 1 minus cosine squared theta. Either one of those would work, because if you turn that a into a 1 right there, minus the sine squared, all of a sudden we got a cosine squared. You take the square root. That's pretty cool. So there's a couple more setups that we can try with this. This is going to be a squared plus x squared, and then we'll try using tangent squared theta plus 1. Notice how it's just like it matches. It's going to be, it would be x squared and then plus 1 over there. So it's the pluses, they match. This is going to be equal to secant squared theta. On this side we have cotangent squared theta plus 1 equals cosecant squared theta. And then we'd have another scenario with x squared minus a squared, and this could use a tangent squared theta equals secant squared theta minus 1. Notice how that fits quite perfectly in there. X squared minus 1. Bam. And then you could say the same thing over here for the cotangent squared theta equals cosecant squared theta minus 1. We're just using the same identities there. But this is for perfect squares, some easy integrals. Make sure to get a couple of these in your little stack. And yeah, I keep mentioning this little stack. I might at some point even make one of these stacks myself and put a link in this video. But this is the idea. You want to build up a little stack of this flashcards with some of these answers already, so that you, like actual integrals, not just put in the theory here. But if you get some actual integrals, you'll start to notice like the patterns and just be like, oh yeah, this was just bam, and then you just get the answer to the integral without having to really even go through all the solution steps. You just kind of know what would solve it, and then you can try to work it out if you have to. Now you might encounter some really weird integrals, like something like this. Here's an example of like 1 over 2 minus sine squared x. And it's like, well, try as you might, you're probably not going to figure out how to solve that one. But if you multiply the top and bottom by secant squared, well, that would just kind of give you the answer. And so, yeah, because then all of a sudden this will become like secant squared on top, and then there's going to be like a tangent, or sorry, what is it? Let's see, this would be 1 over cosine. So yeah, you get a tangent down there. So like, it would just substitute out, and then you could just kind of solve it like that. So that one's a pretty cool one. Yeah. And then maybe there's another one that we might encounter, which is something like this, which is like 1 over 1 plus sine x. And in this particular situation, you might want to use the u equals tan of the x over 2 substitution, which can work sometimes for some of these trig functions. Let's say we had a bigger exponent like on top, so x squared plus 3x plus 5 divided by x plus 1. In this situation, you'd want to set this up. Keep in mind that this is an integral. You want to set this up and do some long division, and you'll get the answer is like x plus 2 plus 3 over x plus 1. Then you can take the integral of each one of these little pieces, and so sometimes you want to use some long division, and sometimes that'll set you up. Once you've got a bigger exponent in the denominator, then you could start doing the other ones like this, 3x plus 2 over x times x minus 2, and then x plus 1. And then you can set this up as partial fractions, and you can go like this. A over x, that's a over x plus b over x minus 2, and then plus c over x plus 1. And then that just solve for a, b, and c, and this stuff is pretty easy. You can also do x minus 2. Setting them up is just a little bit difficult, but once you've got it set up, it's easy to solve it. You know, x squared, and then x minus 1. In this case, you would start like this. You've got your a, and then you want to think, okay, well, I got 2x minus, or here, I'll start with the x minus 1 on this side, so x minus 1, and then I'm going to add, here, I'll just start going like this, so I'll go 2x minus 1, and then I'll start with the squared, and then I want another 2x minus 1, because there's 2, so it's squared, so I'll split this up and do another 2x minus 1, and get rid of the square. And so that way I've got a, b, and c, again, set up like this. Notice that these are just regular old x's. There's no x squared. I know that this whole thing is grouped as a square, but it's just a regular x inside. And so in the next scenario, however, we go 2x minus 3, I guess is what they've got going on there, and then x squared plus 1. This is going to be a over x as usual over here, and then plus here on top, because we have an x squared, we kind of have to add in that whole situation on the bottom, and you get this bx plus c, you know, on top, to account for the x squared. Okay, and then over here, these ones should be pretty easy. Once you kind of get the hang of the partial fractions, it shouldn't be too bad. X squared plus 2x plus 4. Right, this one's a little bit crazy, but essentially we're going to be doing a over x minus 2, and then plus bx plus c, and we've got all of this stuff in there, x squared plus 2x plus 4. And there we go. So this is kind of going to be partial fractions and stuff, relatively simple. Now we're going to take a brief look at infinite integrals. So let's say we had a graph that was going to say, I don't know, from here all the way to here, and this was essentially just trying to go towards infinity over here. But the question is, does it or does it not? And we've got this area that we might want to calculate. So the thing that we might want to say is if it diverges or not. So diverges or converges. What that really means is, does the area inside of this thing, does that area, does it go to infinity? Or does it not really exist? Is it like 0 or something? If that's the case, then this stuff will diverge. And if the area actually reaches a real area, like if you get a real area out of this, and it's like, oh, that's actually a box. You know, this number here at the very end actually hits 0, and that hits 0, and you get like a box. Oh, it gives you a real area. In that case, it converges, so it's kind of nice. Let's take a look. So let's take a look at some examples. Let's say we had the integral from 1 to infinity of 1 over x dx. Now, just because we plug in infinity here, and we actually would get 0 towards the end of this graph, that doesn't mean that you actually get an area out of this, because if you take the integral and you try to solve for this, the ln of the absolute value of x minus the ln of 1, when you plug in, you know, your values here, this turns out to be infinity, because, you know, you plug in infinity right here, and well, you'd get infinity minus 0. So this is going to diverge over here, because the integral reaches infinity, and so therefore the area of this thing reaches infinity. Let's take a look at another example, like the integral of 1 to infinity 1 over x squared dx. And this time, when you take the integral, it's supposed to be, you know, negative 1 over x, and then we're going to plug in the infinity there, and then we're going to subtract it on this side to get that part, but it's actually plus 1 over x on this side, right? On this side we plug in infinity, and on this side we plug in 1, so that will give us the answer of basically 1. And so this one right here is going to converge, because the total area here just turns out to be 1, and so that means that this thing converges. That's pretty cool. Let's try to kind of compare these two graphs on the graph right here, and let's see what would happen. So this one might be labeled g of x, and then this one could be labeled f of x. And so there's some information we can gather from this. Let's say 0 is, well, obviously f of x is greater than 0, and obviously g of x is greater than f of x, right? G of x is greater than f of x. And if that's true, then that means that the integral of f of x is going to be greater than 0, but also that the integral of g of x is going to be greater than the integral of f of x. And we would also be able to say that if the integral of f of x actually equals infinity, this thing hits infinity, then we also know that the integral of g of x also would equal infinity, obviously, because this thing would just push gx out of the way. So if f of x goes to infinity, g of x goes to infinity, and then we would also say that if g of x converges, so if this thing hits 0, then obviously f of x will also hit 0. So f of x will also converge. And, well, hit 0. I mean, if this thing actually each is a real area, it's not really hitting 0. But if this thing hits a real area, then this thing will also hit a real area inside of there. It makes sense. And so these are kind of the things that we can determine based off of divergence and stuff like that. But we're going to be taking a look at that in other videos more in depth. This is more just like the different strategies and tactics that you can use to integrate a whole bunch of these different things. Remember, you want to build up a big list of like flashcards of this stuff. So unfortunately, I wasn't able to save my list, but you know, hey, maybe at some point I'll make a little list of flashcards too. Anyway, if you like this video, go ahead and like and subscribe. Thanks for watching.